Hello friends, today let's solve the binary tree pre-order in-order post-order traversal using iterative solutions. Well, this is a very basic question in algorithms. These three actually belong to the depth first search scope, and there is also a level order traversal, which is belong to the breadth first search, and today we will not cover it. For every traversal, we actually have two types implementation, which is recursive and iterative. Let's briefly introduce the recursive solution first. If the task is ask us to print the value of every node in the tree, for the pre-order, we will print the root value first, and then we go left, then we go right. So the pre-order, in-order, or post-order, the object is the root. Pre-order means we focus on the root first, and then we go left, then go right. The in-order means we will handle the root between the left and right. So we will call the in-order root.left first, and then print the root.val, and then in-order root.right. For the post-order, we will handle these two lines first, and in the end, we print root.val. Okay, this is recursive. How about iterative? The iterative is actually explicitly use a stack, because for the recursive actually is implicitly use a stack. Okay, for the pre-order, we will print the root first. So at the very beginning, we just print this root, and then we go left. And as we use a stack, so actually it's a reversed order. Like if we want to print 1, 2, 3, we need to put 3 before 2. So in the pre-order, we will use a reverse order. We first push the root to the stack, and this is a loop. While this stack is not empty, we pop something from the stack, and then we push it right to the stack, and then we push it left, because in this case we can print the left before the right. Okay, this is the pre-order of this tree, which is 1, 2, 4, 3. So now let's write the order, pre-order. So that will be result array list, and then we first check if root equal to none. We just return result, and then we need to use a stack. So we use a array deck, new array deck, and then we push current root to the stack, and while the stack is not empty, the tree node cur will be popped from this stack. So result will add a current dot value. Okay, reverse order. So if cur dot right not equal to none, the stack will push the cur dot right. And then if cur dot left not equal to none, stack will push the cur dot left. So finally return this result. This is the tree order. Oh, sorry, array deck, not array list. Okay, now let's see the in order. Actually, in order traversal is widely used in balanced search tree. In BST, binary search tree, because if we use in order traversal in a binary search tree, then we will get a sorted list. So this is very important. For the in order, let's see this example. If this is a given binary tree, then we should first print 4, then 2, then 1, then 3. So you will see we will keep go left until it does not have a left node, then we print it. And then we return. So we print 4 and we print 2, and as it doesn't have a right node, so we keep return. Then we print 1, and now it has a right node. We push we print it. If it has, we push it to the stack, and as it doesn't have any node, so we print it. So the core idea of this in-order traversal, we will push the root node to the stack, and we keep push its left node and change it to its left node. So first the root node is 1, and we find it has a left node, then we change it to its left node. So currently the root node is 2, and we keep doing the same thing. So there is a while loop, and then we out of this while loop we pop this node from the stack, and we change it to the right node, and there is an out loop just as the preorder. While this stack not empty, we keep doing these things. Okay, now let's write the in-order traversal. So the same, just code the result array list, and if the root not equal to none, we just return result. And the tree node stack new array stack. Currently we do not push the node to the stack because we will use this while loop. So while stack is not empty, but now the stack is empty, but we need to still go into this while loop just when the root not equal to none. So one of these cases is satisfied, that's okay. So when the root not equal to none, we will push this root to the stack, and we change the root to its left. And now when we out of this while loop, we know the root now will be the stack pop. And we add this value to the result, and the root will equal to its right. So finally return the result. So slow. Okay, let's see the postorder. Actually, postorder, we can change something, modify something from the preorder. Let's first see what's the postorder of this binary tree. That will be 4, 2, 3, 1, because it will print its left and then its right and itself. So let's see. That is root, left, right. This is preorder. This is postorder, left, right, root. How do we get this order? We actually reverse or swap the left or right. Then we get root, right, left. And we reverse this, so we get left, right, root. You can see this example. This is left subtree. It's right subtree and itself. This is itself and left subtree, right subtree. So we can use the idea. We swap it, or actually swap it, and we reverse it. So we get the result. Well, let's convert the preorder to the postorder. In the preorder, we first push the right, then left. So as currently we need to swap these two things, so we will just push the left first and then push the right. And we need to reverse this list. So in the preorder, we add a value from the last. So for in the post order, we add this value from the first, so that implements this reversing. Other part are just remain the same. What does that mean? Actually, we use a linked list because in linked list the add first is big O1 time complexity. This is just equal to push, because linked list can be used as a stack. So push just equal to the add first. You can use push. It's the same. Okay. Sorry. This should be none. When it's equal to none, we return it. When it's not equal to none, we do the other things. Okay. Now let's write the post order. As we need to use add first, so now we use the linked list class. Result linked list. So if root equal to none, we return result. Then we need the stack, right? New array stack. So we do the same thing as we do in the preorder. So we first push the root while this stack is not empty. Tree node cur will equal to stack pop. And we need to get a reverse order, so we use add first cur.value. And in preorder we add the right first. So here we write left first. If left not equal to none, then stack will push the cur.left. If cur.right not equal to none, then stack.push cur.right. Finally, return result. Okay, thank you for watching. See you next time.